phone calls because of balloons.
All right, so we finished the presentation. Great job with that. Almost all of you did relate your design to the impulse momentum theorem, and that was something I certainly was looking for. And I'll get grades up maybe today, but probably not until Monday. So we do have 4 objectives today related to our first glance at waves. And remember, like, this is where we're staying this whole marking period, right? So all the stuff that we're looking at today in next class, and to some extent the class after that, we're going to revisit in greater detail over the next month and a half or so. So we do first want to identify how waves transfer energy without transferring any matter. We want to contrast our 2 different types of waves, our transverse waves and our longitudinal waves. We want to relate a few of our wave properties. And I'm not actually sure we'll get this far today, but we want to discuss wave speed, wavelength, and then wave frequency and how they're related to each other. And then we do want to relate the speed of a wave to the medium that it travels through. So I don't know that we'll get to all those things today. In the other section, we only made it about 2/3 of the way through this second objective. All right, and I do think that you looked at waves last year in chemistry. I know that the chemistry curriculum has changed over the last few years, but I remember kind of sitting in for a lesson on transverse and longitudinal waves and how that related to light a few years ago. So some of this will be reviewed, but maybe not all of it. And what makes this unit different and this marking period different is that so far we've really only cared about the motion of things, the motion of matter. So we had our last homework problem, number 15 that we went over last class. I think we had a bicycle or a motorcycle, right, that moved up a hill. So we had something with mass that moved around. We had projectiles earlier in the year, that's something with mass that's moving around. We had circular motion, that's something with mass that's moving around. We're not concerned with that type of motion this marking period. We're concerned about the motion of stuff that doesn't have any mass, right? So the motion of non-mechanical energy. So a lot of the things that we've talked about are still the same, like speed is speed, right? Now instead of the speed of a bicycle, though, we're looking at the speed of energy that's traveling through something. But we're not going to actually see acceleration very much in this marking period. Maybe that's a good thing for some of you. And even forces aren't going to be all that huge of an issue this marking period. Next marking period, forces will be pretty big again. But we're definitely moving on to a very different realm of physics right now. All right, so to me, right, a wave refers to some disturbance, some agitation that gets propagated through space. All right, and that disturbance is carrying energy, but it's not carrying matter along with it. Okay, just energy. All right, so again, right, our waves are carrying energy through space, but not transporting any matter. The space that our energy is traveling through, we have a name for that. It's called the medium. So whatever the heck the thing is that the energy is traveling, whether it's sound or light or any other kind of wave, right, the material that the energy is traveling through is called the medium. So right now, as I'm talking to you, right, there's sound waves that are leaving me and reaching you if you can hear me. Those sound waves are traveling through the air in the room. So the air is the medium. The light from the overhead lights is also traveling throughout the room, and the air is the medium for that. Ocean waves, right, if you're surfing, bodyboarding, whatever, water, the ocean, would be the medium that energy is traveling through. So medium is just our term for whatever the heck the wave is traveling through. All right, other questions so far about what I've said a wave means or what we mean by the medium before we look at our 2 types of waves? Okay, so our 2 types of waves, as we already said, are called transverse and longitudinal. Does this ring a bell from last year or no? No. All right, fine. Well, there's nothing very complicated about it, so that's not really a problem. In a transverse wave, there's got to be something that's moving, right? That the energy is temporarily displacing as it travels. So in this diagram, we have this arrangement of like red balls and then like rectangles, right, that are linked up, and we initiate a disturbance, right? So maybe somebody grabbed onto this end, right, and disturbed it, shook it. And each piece of this medium is going to move as the energy passes through it, but it is going to move right back to where it started, right? So if I originally grabbed onto this red ball, maybe moved it up and then moved it back down, it does end up back to where it started. So we're not transporting matter. We are jostling matter, we're vibrating the matter, but we're not transporting it. And in a transverse wave, the direction of that oscillation, the direction that the pieces of the medium are moving, is perpendicular to the direction that the energy is going. So in this example, the energy is going to the right, but the individual pieces of the medium are vibrating perpendicular to that. So that's what we mean by a transverse wave. And the only way to properly describe a transverse wave is to compare the direction the energy is traveling to the direction that the particles of the medium are vibrating. Right, so that's a transverse. Let's contrast that to a longitudinal wave, and then we'll take a look at a few videos and then get you guys to produce one of each type. We actually have the same medium here, it's just in black and white, so our red balls are now dashed, and we still have our little cylinders. Now this time, we are still initiating a disturbance in the medium, right? We see something that's getting messed up and moving again towards the right. But this time, we are disturbing the medium, right? Not perpendicular to the way that the energy is moving, but in the same direction that the energy is moving. So a longitudinal wave is classified by the direction that the particles are vibrating is the same as the direction that the energy is moving. All right, I would like to take a look at a few videos, and then we'll ask if there are follow-up questions about the distinction between the two. Hopefully, none of these are private. Have you guys heard of cropping videos, by the way? I saw myself kind of preparing to drop eggs, like way more than 2 seconds times like 20 presentations over the 2 classes. All right, anyway, here is another example of a longitudinal wave. So these dots, I think, are meant to represent, they're meant to represent either atoms or molecules or particles. And what I can if I look to the left side, I see this like gray area that's moving like right and left. That's the source of the disturbance, that's the source of the energy, the source of the agitation. And then that is causing energy to travel towards your right. The individual atoms, though, are moving right and left. If you just kind of set your focus on one individual dot, it's moving right and left. So this is a longitudinal wave, because the individual pieces of the medium are vibrating in the same direction that the energy is traveling. And we can do a transverse wave in this same medium also. So again, it might be a little bit tough to tell with this animation, but the energy is still traveling towards the right, and an individual molecule is vibrating up and down, right? So the energy is going one way, the particles are vibrating perpendicular, that's a transverse wave. All right, let's look at the next one. Come on. Oh, any idea which one just got clicked on. But apparently it's a transverse wave. So what's this one holding? Yeah, it's like a slinky, right? And they're holding the slinky here. We can tell by these red arrows that they're going to move their hand up and down, yet the energy is going to move to the right. So that would be a transverse wave. Like the individual pieces of the slinky vibrate up and down, but the energy is traveling to the right. Can we do longitudinal waves on a slinky? Yeah? Well, let's see. Come on. I think this one actually was pretty slow yesterday too. I'm going to get this fourth one going while we wait. So while we're waiting, let me just share 2 other terms that will get us ready to produce our own waves after we take a look at these last two videos, if this cooperates. Sometimes we refer to a wave pulse. A wave pulse refers to a single disturbance. What? All right, we got something.
That's the same one we just saw.
So maybe this is the one I want. Alright, whatever. So a wave pulse means we just initiate the disturbance once. So for that transverse wave on the slinky, alright, here we go. We'll have longitudinal in a sec. Alright, so of course we can produce a longitudinal wave on the slinky. And to do that, the energy is still traveling to the right, but the individual pieces of the slinky are vibrating right, left. Let's just look at that again so we can convince ourselves that an individual coil on the slinky moves right and left. Certainly does, right? So that's a longitudinal wave. So again, a wave pulse is a single disturbance, and then there are a few different terms for a continued disturbance. I like a continuous wave. The best, I think, Mr. Ziptowitz in your textbook talks about a progressive wave, but that would be repeated disturbances. Now, can I get the last video to come? I might have better luck if I just cut and or copy and paste the URL. The last one, I'm wanting you to tell me which type of wave it is. Oh, so much better. All right, so this time I'll turn the lights off for this one. We have like a rope that gets disturbed. And I'd like you to decide which wave type you think it is, transverse or longitudinal. So it is a pulse, it's definitely a single disturbance. So in your foursomes, can you share whether you think this is transverse or longitudinal, and then we'll watch it again before we say for sure? All right, so I think I picked on this side of the room earlier. Amanda, did your group all agree?
Yeah.
What did you say?
Transverse.
Transverse. I agree that it's transverse, but I think it's a little bit tougher to tell because, really just because of the angle that this was filmed at. I paused it right at the beginning where we can see that this person is kind of holding the string with this hand, right? And then they've pulled up, right, relative to the string, and then they kind of let go. So I think each piece of string we're going to see kind of move down. It's not totally down because of the camera angle, but the energy is clearly moving this way. And then I think that each piece of string is moving perpendicular to that. So let's watch it one more time. Right, so the string starts up here and then it ends up down there. That's like perpendicular to the direction that the energy is moving. So I think that's definitely a transverse wave. Other questions about the distinction between transverse and longitudinal waves before we spend 5 minutes, 8 minutes making some? Okay, great. So let's actually meet right behind where like Janelle and Ruchi and Jack and Emily sit. And I'll meet you back there in 2 minutes.